Unit 20, Electrochemistry, pages 275 to 278, focusing on assigning oxidation numbers. Electrochemistry is electrochemical reactions that involve the conversion of chemical energy into electrical energy. Batteries are an important tool in modern society and are based on spontaneous electrochemical reactions. Electrical energy can also be used to drive chemical reactions to produce useful products. Aluminum, sodium hydroxide, and chlorine gas are typically produced using electrochemical reactions. So uses of batteries, cell phones, calculators, computers, pacemakers, cars, all come from electrochemical reactions. So our focus is on what's called oxidation reduction reactions, or for short, redox reactions. Oxidation reduction reactions are sometimes called redox reactions for short. These type of reactions involve electrons being exchanged between the reactants. Some examples of redox reactions are corrosion, rusting, batteries, and electroplating, where one substance loses electrons, and that's called oxidation, and another substance will gain electrons, and that's called reduction. So there's an acronym for this. LEO goes GER, to help you remember that lose electrons is oxidation and gain electrons is reduction. So we have to be able to assign oxidation numbers in order to know who's losing electrons and who's gaining. So oxidation numbers are a bookkeeping method to keep track of electrons. The values don't always relate to actual charges on the atoms. For ionic species, the charges reflect the actual charge on the ion. In molecules that use covalent bonding, the oxidation numbers do not represent actual charges on the atom. So here are the rules for assigning oxidation numbers. An element in elemental form has an oxidation number equal to 0. So if you have a single element or a diatomic, which is its normal form, then these are going to be assigned an oxidation number of 0. And we write it as a superscript above. So each of these would get a 0. A monoatomic ion oxidation number is equal to the charge on the ion. So you see how this one already has the plus charge assigned to it? It's telling you that its oxidation state is a +1. Or because this is already assigned with a -2, that is its oxidation number. Remember that ions like hydroxide are polyatomic ions. Compounds with two elements. For PCl3, chlorine is the atom with the greater electronegativity. So it's going to have its oxidation number equal to the charge when this atom forms an ionic compound. So since chloride normally is a -1, then it's going to be assigned a -1 in this compound. Because there are 3 chlorines, I would have 3 times -1 is an overall -3, which means to balance that, the phosphorus must be a +3 overall charge. The chloride in sodium chloride has a -1 charge, so the oxidation number is -1. So if you look on the periodic table, anytime you have an alkali metal, it's going to have a +1 oxidation number. An alkaline earth metal will have a +2. These, of course, have varying oxidation numbers that you'll usually get told. These are going to have a +3, and then over here you're going to typically use -1, -2, -3, unless of course there is a change in electronegativity comparison between the two elements. For CO2, oxygen is the most electronegative element. In the ionic compound, Na2O, O has a -2 charge, so the oxidation number is -2. So here, I would assign oxygen a -2 charge, and then I'd say 2 times -2 is an overall -4, and so to balance that, this carbon must be a +4. Here, because sodium is in group 1, it would get assigned a +1, and normally you would assign this a -2, and luckily that works in this case because 1 times 2 is an overall +2, which must be balanced by an overall -2, which we do get from this oxygen. So oxygen is usually -2. There are some exceptions, one of which is if it's in a peroxide, O2 - 2 overall. That means that each oxygen actually has a -1 charge. So in this example, you would assign a -1 as the oxidation state on the oxygen and a +1 on the hydrogen. 1 times 2 is a +2 overall, and -1 times 2 is a -2 overall. This is the only way the charges would balance. You could not give this a -2 because hydrogen could never be anything but -1 or +1. So peroxides will have a -1 charge. But otherwise, oxygen is going to have a -2. Hydrogen is usually +1 as long as it's with nonmetals. But if it's with a metal, it's a -1. This can get a little tricky because, for example, if I have sodium hydride, IDE, then here the sodium has to be +1, and therefore to balance it, the hydrogen would have to take on the -1 charge. But if we had other elements in the compound, like sodium hydrogen carbonate, for example, well then the sodium's a +1, but the hydrogen doesn't have to be a -1 because oxygen is the more electronegative element and it can harbor the negative charge. So here we'd have 2 times 3 is -6 overall, and so the hydrogen could still be a +1, and then the carbon would be +4 because 4, 5, 6 gives me my overall +6 that balances this -6. Fluorine is always going to be a -1 charge. There is no exception. And the sum of the oxidation numbers must be equal to the charge on the ion or the molecule. So find the oxidation numbers for each atoms of these. So we'll start with PCl3. And because chlorine is more electronegative, we're going to go with its normal charge on the periodic table, which is a -1. Overall, this gives me -1 times 3 is a -3. So to balance that, the phosphorus must be a +3. Remember that everything should add up to equal 0 since this is a neutral molecule. All right, for permanganate, we have MnO4 and an overall -1 charge. So all of my charges together have to actually sum together to equal -1. So what I'm going to do is assign my oxidation number to oxygen. Each oxygen will typically be a -2 charge. 2 times 4 is an overall -8. So the manganese must be a +7 because a +7 combined with -8 equals -1 overall. And so the oxidation states would be a +7 on manganese and a -2 on the oxygen. The last one is the cyanate ion, which is also overall a -1 charge. The oxygen is going to get a -2 charge. Nitrogen is going to get a -3 from the periodic table, and together these make -5. So the carbon must be a +4 because +4 and -5 equal my -1 overall. This one would have been rather challenging, but you just have to remember the typical charges that you would get for oxygen and nitrogen on the periodic table based on the family they're located in. So here's your note card. Pause the video and copy it down. When you assign oxidation states, any element on the periodic table in group 1, an alkali metal, has to be +1. Group 2 +2, group 3 +3. There is no exception to these, so they are something that you can label first. Fluoride can only be a -1. Now hydrogen has two possibilities. Hydrogen is typically a +1, but if it's with metals, then it's going to be a hydride, which means it should be a -1 charge, such as in this example here, sodium hydride. Oxygen, or oxide, is going to typically be given a -2 charge unless it's in a peroxide, in which case it's going to get a -1 charge, such as in the example of hydrogen peroxide. Single elements and diatomics equal 0. So you're going to just give them a little 0 above them because they're neutral. The sum of the oxidation states in a compound have to be 0 if it's neutral, and the sum of the oxidation states in an ion must add up to equal the overall charge.